So we have seen that in the arrangement of speed control of an engine, we have all the blocks connected in series like this. So we have the throttle block, here we have the power stroke block, then comes the final combustion. After combustion, the engine is going to generate some torque, which is called the engine torque, and engine torque will be compared with the load torque, that is called the vehicle dynamics block, and here you have the final speed output in RPM. So when you connect all these blocks in series one after another and then apply a controller in the feedback loop, that is going to become your entire process control. So this is a vehicle control application we have seen, and this vehicle control application is controlled by this PID controller. So we want to learn about this controller. So this is a speed control for an engine application. Now in case you have a battery electric vehicle, and that battery electric vehicle is going to have for example a DC-DC converter over here, then a motor electrical equations, then you have the motor mechanical equations, and then you have finally the torque and speed or vehicle dynamics, where you have wheel or the road characteristics, and finally you are going to get the output speed of the vehicle in kilometers per hour, for example. So in this case, you want to control the duty cycle of a DC-DC converter, right? So this is a similar case where we want to analyze our system which is cascaded together, right? So we have an equation of a DC-DC converter where we can represent this block as V in and V out, right? Or the ratio by VO to V in, and that is nothing but the duty cycle D, which is on time divided by total time T. Now over here there may be some other equations over here, there may be another equations over here and another equations over here. So if we put all the equations in a block diagram format together, then what we are required to control? We are required to control what should be the value of the duty cycle in such a way that to obtain the required speed as per the speed reference or as per the throttle input. So we can apply the same situation to the case where it is electric vehicle. So for simplicity, I am considering the built-in demo of the MATLAB, in which we have already seen that how this PID controller makes the engine RPM smoother or without any pulses. So this particular block is going to initiate the action, or this block is nothing but of very important to us, right? So you will find in most of the models of electric and hybrid electric vehicle these kind of blocks. So we are interested in learning about these blocks. So what is the purpose of using this block? This block is going to make the control possible, right? This block is going to make the actual engine speed trying to trace the speed reference, right? So who is going to follow the reference? This controller is going to take the action in such a way that this throttle is going to change and the vehicle speed is going to either increase or decrease, right? So this PID controller here generates the throttle angle command, which is very important for speed of the engine. So in this case, we have seen that this PID controller was used for this particular application, and we have seen a block of PID controller as well. So this is a block of PID controller, and here you see that all components which are P, I and D are given by this compensator formula. So this is P, which is proportional, integral, the 1 by S stands for integration, and D is a derivative coefficient with the filter coefficient N. So if you put all these values of P, I, D being 0 and other values and this initial conditions, you are going to actually fine tune your engine, right? So how the engine is fine tuned? Engine is fine tuned in order to follow the reference, right? So the reference is followed by this particular PID controller block. So this PID controller block is very important. And now instead of trying with all these values, what we did, we just click on the tune button. So this tune button is going to actually do a process in the background. So what process is going to be done in the background is choosing the value of all these components, P components, I component and D components, in such a way that the desired response is obtained. And this particular process happens in automatic mode, and this is called auto tuning, right? Obviously the user can adjust some of the parameters like the robustness and the quick responsiveness of the system, but overall this calculations of all these parameters are done automatically in the backend by the MATLAB. So what is this process and how it is done? Now if I use PID controller, right, for example in a circuit where it is a battery charger, so if we use this PID controller in a battery charger, then the transfer functions or the plant model will be different, but the same controller with all differently configured values can be used to control the battery charging as well, right? So this PID controllers are going to be used for both electrical and mechanical systems. So these controllers are very much important, and we want to learn about this controller. So in order to learn about this controller, we need to see a control system theory a little bit. So let us deep dive into the control system theory and understand what exactly is the meaning of this PID controller and what are the changes it is going to make to the system. Let us learn about this particular controller and this control actions. So before we learn about them, we need to have enough background of control system engineering. So let us create the background of control system engineering before we directly jump into the tuning of PID controllers. So the frequency response analysis is the first step in learning the PID controller tuning. So what is a frequency response analysis? So this response analysis is based on different frequencies over the period of time. So we apply different frequencies to the input and analyze what is happening in the output, and that is called a frequency response analysis in simple words. Or in other words, we can say that the steady state responses of the system when it is subjected to the sinusoidal inputs. So when we considered step input, we actually considered this to be equivalent to wide open throttle speed reference, right? So the step response or the step change in the speed is equivalent to wide open throttle in case of electric or hybrid electric vehicle terminologies. Similarly, when we say the high frequency, we are going to consider the sinusoidal analysis. So we are going to apply now other than DC functions. So step and ramp, we can say that those are DC functions with some constant coefficient and the slope value. But now we are also going to learn about what is going to happen when we apply AC input quantities to the system. So this frequency response analysis is based on the sinusoidal. For linear and time invariant systems, the sinusoidal nature remains the same. So if you give sine as input, you are going to get sine in the output. So that is the nature of the LTI system, linear and time invariant system. So then you may be wondering that if we give sine input and if we get sine output, what is the change the system is making over here? So yes, there will be certain changes. They are not going to be exactly equal, but their nature, or we can say the frequency, remains same, or their sinusoidal nature and the frequency are going to be same. So what are the changes? Changes are only in amplitude and phase, right? So for example, if I draw a typical sinusoidal input and a typical sinusoidal output, let's say this is the input we are applying to the system, and let me draw the output with the black pen, and this output is, for example, like this. So let's say this is the output of the system. So with this input and this output, what we have observed, so this is input and this is the amplitude of the output. So when we consider their values or their amplitudes, it has changed, right? So the amplitude has decreased in this case. So it can either increase or decrease compared to the input with reference to output. What has happened to the phase? So here you can see the phase is 0, and there is a time lag between these two. The frequencies are same, but there is a time difference, or we can say the phase difference between two. So the amplitude has also changed and the phase is also changed. So the phase can also either increase or may get delayed or may get advanced, right? So the amplitude may get increase or decrease. So now if we understand what is happening to amplitude and phase, we can say that what is the nature of the system, and we can predict the behavior of the system, right? So the frequency response analysis is, in simple words, applying different frequencies to the input and observing in the output, and then concluding the important remarks based on the changes in amplitude and phase, right? Now you may be wondering that one time we have considered the step response like this. So this is a step response or the step input, and then we are considering the sine input, and then how we can correlate this step with the sine and like that. But ultimately, if you consider the fundamental behavior of the signal, a signal which is DC or step in nature can also be expressed as multiple sinusoidals superimposed together, and that is what is known as a Fourier series, right? So the Fourier series is nothing but this DC signal is actually the summation of all different frequencies component with the different amplitudes, right? So even if we consider zero frequency, that also can be analyzed with different frequencies, right? And similarly, the same is true in case where we are learning about the inverter which is operated from the battery. We can also build up the sine waves from the DC battery voltages by sine PWM, right? So this analysis, when we consider the sinusoidals, it also includes the DC by default, right? Or when we say that the frequency is set to 0. So if we set this frequency component to 0, then we can call it as a DC analysis.